So let's look at another example of a direct proof. All right, this one's a little bit different because of the very beginning of the statement. All right, so it says this: for all integers n and m. All right, so that just means that we want to make sure that we don't pick a particular n and m. It's for all integers. All right, then it says if n minus m is even, then n cubed minus m cubed is even. And so what comes after the then should be my very final statement. All right, so that should be my conclusion. All right, so let's go through and let's see exactly how you would write that up. First, I would say, proof. So first we need to do our setup. So we have to make sure that we have two integers. Okay, so let's start off by saying assume m and n are both integers. And that's a perfectly fine way to write that. Just put a comma between the letters and you'll know that both of those are integers. And that n minus m is even. Now you'll notice here that they left off the word integer, but whenever you talk about even and odd, we're going to assume that we're talking about an integer. And I guess that would be automatic anyway, because if m and n are integers, we know if we subtract two integers, we get an integer. And then just like before, we need to say, okay, what does it mean for n minus m to be even? All right, so let's just say by definition of even, there exists k that's an element of the integers. Now, it wouldn't hurt if you used a subscript here, but notice that I don't have anything else to do with another integer, and so actually I can just get by with just using k. All right, so by definition of even, there exists a k that's in the set of integers such that n minus m is equal to that 2k. All right, so then let's look and see, if you haven't already, like what it is that we're aiming for. We want to show that n cubed minus m cubed is even. All right, so what that means is I want to be able to write this number as 2 times some integer. All right, and it doesn't matter what that integer is. It just has to be 2 times some integer. All right, well, I guess let's just go to the n cubed minus m cubed and see if we can get anywhere with that. So I'm going to say then, I could say so. All right, so then n cubed minus m cubed is equal to. All right, well, I know that n minus m is even, and I can write n minus m as 2k, so it sure would be helpful if I could write this in terms of that n minus m. Unfortunately, we can do that. From way back in algebra, you learned that you can factor this. It's the difference of two cubes, and you can rewrite that as n minus m times n squared plus mn plus m squared. All right, and so then I look at this and I say, okay, well, is this helpful? Well, sure it is. I know here I've got this n minus m is equal to 2k. And so what I can do is I can substitute for this n minus m down here. I can put a 2k in the place of that. And I believe that's going to help me out here. So let's see. We know that that means that this is going to be equal to 2k times n squared plus mn plus m squared. And that was really just by substituting the 2k in the place of the n minus m. And so remember what we're aiming for. We're trying to be able to write this n cubed minus m cubed as 2 times an integer. Well, we just want to know, is this 2 times an integer? Well, it's certainly 2 times something. So let's rewrite it as 2 times k times this n squared plus mn plus m squared. And so the question now is this right here an integer? All right, well, let's see what all we're doing. Okay, first we know that everything in there, the k, the m, and the n, individually are integers. And what we're doing is we are adding and we are multiplying, all right, and maybe in different orders. So we know that for integers, it's closed under multiplication. It's also closed under addition. And because that's the case, then, of course, this is going to be an integer inside of the parentheses here. So now we just need to be able to say that what's inside the parentheses is indeed an integer. And so here we will say, by the closure property of integers under addition and multiplication, then we have this k times the n squared plus mn plus m squared is indeed an integer. And so then we really have it. We can say, okay, well now by definition of, remember we're trying to show that it's even, so by definition of even, this thing right here, this m cubed minus m cubed that we wrote as 2 times an integer is even. And so really we're done there. If you want to write the final therefore, it's fine, but I hope you see that in this particular case you just really ended with n cubed minus n cubed is even. It won't always be that case, so typically in a proof you would see something like therefore n cubed minus m cubed is even. I'll put it here just for emphasis for right now. But that would be the end of your proof here. Now this one may not look too bad, except for maybe the handwriting, but may not look too bad. You could even turn this in as your final. You may find ways to clean things up, and if you feel that you can, please feel free to do so. Also feel free to send your work to me. So like if you have a problem that you're doing, and sometimes in the beginning, especially when we're talking about even and odd integers and that's so intuitive to you, you may leave out some of the details. So feel free to send your work to me and I'll be glad to look at it and say, oh, you really needed to say by the closure property here, or whatever the case is. So now let's talk about disproving universal statements. And the only thing we mean by universal statements are all the kinds of examples that we've seen prior to this. So we've seen things where we had to prove something like for all integers n and m, if n minus m is even, then n cubed minus m cubed is even. So that's an example of a universal statement. Well, if we ever want to disprove a statement, a lot of times that's actually a little bit easier than trying to prove one, and that is that you just have to find a counter example. All right, so if you want to disprove something, just find something that doesn't work. All right, so here's an example. So let's say that it says for all integers m, if m is greater than 2, then m squared minus 5 is even. So let's look at what this is telling us. The first part says for all integers, so it looks like, it could be positive, negative, even, odd, whatever. But then if you look just a little bit further, it says if m is greater than 2. All right, so now we're restricted a little bit more. So the integers greater than 2 would be like 3, 4, 5, and so on. All right, and then what we want to do, since we know that we're trying to disprove this, we want to find one of these numbers in here such that this m squared minus 5 is not even. All right, so we want to find a counter example. So can we find a number to plug in such that m squared minus 5 would not be even? All right, well, let's see. If m equals 3, then what we have is 3 squared minus 5, which is 4, and that's even. So, maybe there's a chance it really did work, and I just messed up here. Let's try m equals 4. All right, if I do m equals 4, now we get 16 minus 5, which is 11. Oh, and that's odd. Okay, so what we have done here is we have disproven this statement because we were able to find a counterexample where it was an integer, it was greater than 2, but m squared minus 5 was not even. All right, and so our counterexample, again, you only have to find one. But ours is that when m equals 4. And so we would say that this is a false statement. And here's our counterexample. Now, it may be that you can describe the counterexample in terms of a group of numbers. In fact, you probably can see that, if you have an even number minus an odd, that's going to be odd. So really, if m was any even number, it's not going to work. So, if m were 6, then you have 36 minus 5. And so that's going to give you 31. 8 squared minus 5. 10 squared minus 5. All of those. But you just have to state one. So now let's look at this last one. It says, for all real numbers x and y, if x squared equals y squared, then x equals y. Now first it says for all real numbers. All right, now real numbers are just any number on the number line that you can think of, just not the imaginaries. All right, so it could be positive, negative, rational numbers, irrational numbers, just basically anything on the number line. So it says x squared equals y squared, and then we want to know, does that imply that x equals y? Well, I think you can probably think about if you had maybe a positive number and a negative number, that you could have the two equal to one another because you're squaring it. All right, so let's just say, what if x is 3 and y is negative 3? All right, well, we certainly can see that, our x squared does equal y squared, because we would have, 3 squared equals negative 3 squared. But the question is, does this imply that x equals y? And in this case, we have 3 equals negative 3, which we know is not true. And so that doesn't work. And so our counterexample here would be the x equals 3 and y equals negative 3. And so we can say it's false. And I'll just say counterexample. And we have the x equals 3 and the y equals negative 3. Now for your homework over this, I'd like for you to read page 128. There's some definitions, basic definitions you've probably heard of before, but you'll have to make sure that you understand the way it's worded so that you can do maybe a couple of the proofs in the homework. And then on page 139, you'll do the problems that are listed there. One thing I do want to tell you is that, the problems that we just did where we were disproving something, the way it's worded in the homework is you'll have to decide whether it is not true or true, and then if it's true, you'll prove it, and if it's not, you'll provide a counterexample. So I know a lot of times, when I see a statement that looks like a universal statement, you just start trying to prove it, and you forget about the fact that, maybe it might not be true. So just don't forget about that. I would kind of think through some scenarios. A lot of times, positive and negative numbers can interact in a certain way, or maybe there's special numbers that make it work or don't make it work. So think through those things before you try to prove it if you think it's true.